Okay, so I don't have the homeworks graded, but I do have your test graded. I was gonna wait and go through that on Thursday, okay? So if you wanna see what you got, you can come in and talk to me. I still might actually give you a problem, say, do it, need some extra points. Some of the multiple choice was kind of scattered, like maybe 3 people missed one question and then 3 people missed the other one, but that's like 20 points. And I'm like, okay, that's not quite the way I wanted it to go. So overall, I think you understand the concept. I think you just missed one little aspect of it. So I was actually happy with the test. I was happy with kind of the outcome of where people were. It's just, if they would have just answered this one question right, they would have had 20 more points, you know what I mean? So I don't think that's quite fair, so. I don't know, when I was grading them, I was very surprised, not surprised, but like, okay, you're actually, you kind of know what you're doing, so that's good. So the plan right now is to kind of continue what we're doing, but kind of more of, you remember the fan problem on the last homework? We're going to look at angular momentum. And so we're going to do this problem. We'll do as many problems as we can today and next class. And then we might have probably a work day, but it might be, I cover one little concept first and then a work day. And then I'll probably have another test. But that's a few weeks away. So. But right now, for today and for Thursday, we're going to cover this stuff. Okay, I'll post. I don't know if I posted the new homework, but I will. It deals with stuff like this and another problem that I'm going to give you that we'll go through. Okay, but I probably will have a work day. Let's see, next Thursday. We'll probably come in here first. Okay. Everyone else got one but you? Huh? Oh yeah, you need one. I thought there was one more. Now if this keeps acting up, I don't know why it's doing this. Okay. All right, so let's go ahead and let's do this problem. So we'll spend today and Thursday working on this stuff. Come in after break. We'll have one day next week, right? Which is Thursday. Come in here. I'll go through one last easy concept, and the rest of that time will be a work day. Okay. So let's go ahead and do this. So we have. What is it? What does it say? Just grain? Yeah, okay. Yeah. So grain falls straight down, hits this conveyor belt, goes down this conveyor belt, and spits out at the end. Okay? And what we're trying to find is, what are we looking for here? Determine the reaction forces. Okay? So what I'm going to do is we'll set the problem up, and then we can go through numbers if you want. But really, the biggest thing I gave this as a test a couple years ago, is how do you set this problem up? All right. So let's go ahead and do a sketch. I'm going to start right at C, kind of curve down. So we're doing a control volume. So I guess if you want, you can just kind of do a dotted line. But we're really kind of doing a free body diagram on this shape. Yep.
Oh, excuse the bridge is dumb.
Maybe his plane ran out of fuel.
Yeah.
Okay, so at point C, what type of forces do we have? Wrong.
Pinned. Yeah.
It's a pinned, so we have what? A B. Roller at B. It's hinged at C, right? Does it say that?
Yeah.
Yeah, hinged at C. So we should have
and
I was waiting for someone. So CX and,
C1.
oh, hey, I didn't know I could do that. So CX, CY. Oh. Sorry, Devin, I didn't mean that. I just was hoping someone would say that and be like, yeah, I got him. But that's good that you spoke up. But at B, there's only what? Just the vertical one. I'm going to call this FB. Or you want to call it CB. Doesn't matter. I don't think it matters. So we have the reaction forces at C. We have the reaction force at B. Might as well put the weight force in here, right? And that X here. And that's W. Then might as well label here. This is in. And then we have something coming out. And what I'm going to do is I'm going to split it up into two components. So we have, oh, I don't want to do it that same color. Why didn't it switch? Here. And, oh no, we can leave that. We'll just do it at that angle. Was it 10 degrees?
Yeah.
And we'll just label that out. Because sometimes it gets kind of cluttered. So 2. All right. So we labeled the forces on the left side of the equation, and then we labeled what's coming in and going out. All right. Here you go, dude. All right. So our basic equation, start with out minus in, right? And we know where there's two directions. So we'll do X direction. And I'll zoom out just a tad. Is that okay? So I think all we have is CX, right? And let's make those directions positive. So X and Y. So CX. And actually this whole term goes away, right? Because control volume isn't moving. What's coming out in the X? Well,
FBX. FBX.
Oh, you mean this right here?
Yeah.
Yeah, I'm just going to call it M dot 2 V2X. Is that okay? So this is a velocity coming out, and we're going to do the component of it, which I think is, I didn't do these numbers, but that's fine. It would be cosine. And the velocity is going to the right, which is positive, so our sign convention is correct. So let's do the y direction. We have a lot of these forces, right? We have CY, we have plus FB, we have minus W, and we'll set that equal to
So we're
something.
not neglecting it.
Nope, not in this one. Nope. Knowing that the combined weight of the chute and the grain. Yep. Yep. So we have to combine it. 600 pounds. Yep. So we got all the forces. Now what's coming out in the Y? We have m dot 2 times what? A negative V2Y. So this is coming out of our control volume. This brown vector, I can actually, why don't we do that right here? And so this is V2X, and that's V2Y. And I put the negative because it's downward, with our coordinate system is up. Anything else going out? No. Then we have subtract m dot 1 times what? A negative V1. And we already know that's in the Y direction. Because that's straight down.
Well, we have to use sine for V2Y.
Yep. So I'll write that down next line. And let me put the negative in front here. Negative m dot 2 V2 sine theta plus m dot 1 V1. So again, always remember that keep an eye on your sign conventions for your velocity because they're vectored. The mass flow rates are just rho AV. Okay, there's no component in that velocity for that velocity. It's just the amount of mass coming out of that section in that control volume in that direction. So, basically, this is a good review of what we just covered. Okay, hopefully it even makes more sense now. All right, actually looking at the test I was telling everyone earlier, I was pretty happy with the outcome of it. So there is some of the multiple choice that probably were worth more than I probably wanted to. So I'm going to probably give you a problem, say, do this problem, get some extra points. Okay, but this is a good review. So we're stuck here, and we're looking for CX and for CY. But we don't know what. Let's go over here to the red equation.
We don't know C.
We don't know. Well, could we find CX?
Well, yeah.
We could find CX. Okay, so that's doable. But over here, could we find CY? Do we know FB? No. So then we're stuck. Okay? So what do we need to do? What have you done in statics? Moments. Where are we going to do a moment at?
B. At 2 because 2
Well, if you do it, okay, this is
Well,
good. So if you do it at,
You can't do it. I'll find it.
exactly, yeah. So don't do it at B because that's what you're looking for. You want to do it at A. So we're going to sum the moments at A. Or is it C? Oh, C. Yeah, sorry, C. Yep. That's stupid. They should have had an A, B, C.
Well, they go to G.
Or they go to G. Don't ask me. So this is the equation that you should have used on the last homework set, which I need to look at. And we're going to find the moment at C, right? Okay, C.
You looked at the equation before you.
Sorry. Which way do you want? Actually, I'm going to pick because I did it this way. We're going to assume this way is positive. Just throw some stuff. So again, if you noticed, I don't put on our free body diagram, I only put the external or the forces that need to go on the left side of this equation. Same in here. So what's your first moment? SC. That's on the right side of the equation. So that's so the weight force. The weight force. Yeah. So that's going all the way around this way. So it's a positive moment, right? So we have W, and what's the distance? 7 feet. Yep. Those, yes. Yep. Next one. Well, that's on the right side.
Right.
That's the. We just. I think, you yelled at him for doing it.
Yeah. Well,
Then you slapped him for yelling back at
I
you.
wanted to imply that he was stupid.
No. So what's the next force? Yeah, minus FB, thank you, times 12 feet, yep. Okay, so now, if you look here, we got to do, what do I have? It should be out, so I have m dot 2 times v2y times what? Does everyone see that? I had to split out this component because it's shooting upward or downward, right? But what's that distance from point B to 12, right? Does everyone see that one? Because, I'll draw it over here, this velocity, I'll make it nice and yellow, how about that? So this has this component, and then this one is down, right? So, yep, that would be 12, and then what would that distance be? For X? 6 feet, yep. And that is a negative or a positive? The Y, this moment would be positive. The other one should be, yeah, because we don't never go that way, so that one's going to be negative. Yep. Yep. So that's times 12, and then we have a minus. Oh, you don't want yellow. A V2x times 6, and then we subtract what's coming in for the moment,
Well,
which
can we
is
just put brackets around the first or
Yeah.
second, please?
we can do that certainly, and I'll put this minus as in blue. Yep. And then this should be m dot 1 times v1 times 3 feet. I'll be correct on that one. And that's a positive moment, but it's, remember, the equations always subtract in. So that's cool, right? And we can use this moment equation to solve for FB. And it's very similar. Yep. Okay. I'm not gonna. I can give you. I don't even know if I have the answers. Let me go back, and I can give you the answers and finish this. But this is really the biggest thing, is knowing how to set this problem up. Okay. So
600 times 7.
So let's just recap this. So over here we have grain falling into our conveyor belt, going out, and then it shoots out at 10 degrees. What we did is we did a control volume on the grain, We labeled all our forces acting on our control line. Okay, so we have the reactions at C, we have the reaction at B, we have the weight, and then I labeled our velocities coming in and going out, which is 1 and 2. All right. This out has two components, X and a Y. All right. So when we did the X direction, we only had CX, which is our reaction force on the left. And then the right side, we had only going out. So we had m dot 2 times v2x. We split that velocity into a component. Okay? So we ended up getting v2 cosine theta. Then, in the y direction, we have three forces on the left. Remember, those forces that you draw on your free body diagram could be pressure, weight, or reaction forces. Okay? I didn't do any pressure forces. How come?
Because they're all capable. Because it's all open.
It's all open to the atmosphere. So pressure acts on the top and on the bottom, and it all cancels each other out. Okay? All right, do you guys remember when you did the hydrostatic forces in fluids? You never had to worry about atmospheric pressure because it acts on both sides of the dam and they cancel. So there's no sense of really putting it on the diagram because it's just all going to go away. Okay? So again, you could have pressure forces, you could have reaction forces, and weight forces, which are called body forces. Okay? Then on the right side, in the y direction, we have one going out, but this velocity vector is negative because it goes downward. And then we subtract what's coming in. And again, this velocity vector is negative. That's why we have negative. So we end up with a positive here. We have the negative here. And then we find out that we can solve for Cx. However, we can't solve for Cy because we still don't know Fb. And what we need to do is do the moment at point C and actually solve for your Fb. All right. So this is angular momentum for fluid flow. Okay. The very first problem in your homework, actually I can show you. It is recording. Good. Just gonna give you an idea what the homework's looking. Angular momentum. Wow, we're only in homework 5. I don't think it is. I need to fix that. Yeah. Yeah, week 5, yeah. So there's 3 questions.
Have we done something very similar to that?
This one?
Yeah, this one seems familiar.
No, but you probably did one kind of similar, probably last homework. Yep. So this one, you have a hydrant, water comes in the Y and shoots out in the X, but over here shoots out X and Y. And I believe it wants to find,
I've never seen fire hydrant.
no? I don't know.
It's gotta be European.
Determine the horizontal and vertical reaction forces, okay, which occur down here, Cx, Cy, and the moment generated down there. Okay, so that's question 1, which is you're going to do the angular momentum. Yep, you might have to do some of the forces too. Yep. So that's problem 1. Okay. Problem 2 we're going to go through here next. I think this last one is MATLAB, but I'm going to probably give you a couple days to work on stuff. Well, she's trying to slide.
Backwards?
Yeah. So what's usually skates on ice we can assume frictionless. So when she turns this on, she moves at a constant speed. That way. Okay. Constant speed means no acceleration.
Come on, Will.
Okay.
But
There's no friction.
Yes, but initially yes, but we'll assume after that don't worry about it. But I'm going to go through a problem like this with satellites, and I'll give you one. Okay, one example, and you apply it the same way. This one's actually pretty short. compared to number 1. Okay? Then I don't know if we might start one of these problems, but you're going to get pretty much, we're going to do one exactly like this, but maybe with slightly different numbers, so you have it all done. I just want you to change some numbers, I believe, and then plot it. Okay? But when we get to this one, you can. So this is a sprinkler. Water comes in, out of the page, shoots out, and you want to figure out what the length of each sprinkler. No, I want you to find the RPMs, and I think that's all we're doing. Yeah, trying to figure out how much water you put in, how fast is this going to spin, and depending on what these angles would be. Okay. Yeah. So I haven't updated it yet, but these are going to be your 3 questions. Of last year, Will. So you're late. Okay. Let's go through.
Time yet again, Will. Oh man, you're on top of it.
You have to go back in time. Okay, so let's do this one. Now the printer printed it on back both sides because I asked for 12 copies and it printed 6. I print 12 more.
Yeah, why does it do that?
I don't know. You can't change it. Delete it. So we waste more paper. Think about it. Well, ink, I guess. Not the same as paper.
By trying to force the conservation of paper.
What's the matter? All right, let me get this up. Week 6. Nope, wrong one. Go to this one. Week 6. Day 2.
Oh, it's like around scale chapel. You're right. You're so bad.
Okay, so we have an orbiting satellite, has a mass of 3,400 kilograms and is traveling at a constant velocity. To alter its orbit, attached rocket discharges 100 kilograms of gases from reaction of a solid fuel at a speed of 3,000 meters per second relative to the satellite in the direction opposite of the Earth. The fuel discharge rate is constant for 3 seconds. Determine the thrust, the acceleration, and the change of velocity. Okay. What's that? Yeah, I mean, and then actually it's not too difficult to analyze. So here, let's start right with the force equation that we have. Yes. So we can't, well, let's go on the left side first. We're in outer space. Now,
There's no gravity.
we're assuming that our laws and people guesses are right and there's an outer space. There's no reaction forces. There's no forces at all in outer space. Okay? So this whole term on the left is 0. Yeah. Yeah, you have 0 vacuum X everywhere. Sure. Okay. There's no friction forces. There's no pressure forces. There's nothing. Okay.
There's no gravity. The world's flat.
Yeah. Well, we're not even worry about that. We got to leave this term in because it's accelerating. And is there any fluid coming into it? No.
No.
And there should be only probably one going out, right?
Yeah,
So which way is this satellite moving?
to the right.
To the right. So we have plus m dot out times what? Positive or negative?
Negative.
Negative, yes.
I hear that.
Because the satellite's going to the right, and this gas is going to the left. So that's a vector, so it has to be this sign change. Okay, so if I bring the MA term over, and I keep this like this, oops. The thrust that's generated is just your mass flow rate times velocity. That's what thrust is actually defined as. So anytime you have a rocket
So
or
you're considering MA as
or I would say yes, it is in this case,
thrust, right?
but really mass flow rate times velocity is thrust.
Okay.
So if you have a rocket and it's shooting straight up, if you know your mass flow rate of the gases being expelled and the velocity, that's the amount of thrust. Okay? So that's what we're looking for. I gave you the velocity, right? Yep. So we need to find m dot. How do we find m dot? So the fuel discharge rate is constant for 3 seconds. How many kilograms in 3 seconds? This is to alter a test rocket discharges 100 kilograms. So this thrust would be 100 kilograms over 3 seconds times 3,000 meters per second. And we get a thrust of 100 kilonewtons. Isn't that crazy?
That's our answer to A.
That's the answer for thrust. Yep. So, because you know mass flow rate is mass per second, right? Yeah, in 3 seconds. Yep. So 100 kilonewtons of thrust. That is a lot. But it's shooting out at 3,000 meters per second. I don't even know what that is in miles per hour. I don't know. That's pretty fast. 2 million? Wrong. Come on, Will. Your turn. Your plane doesn't go that fast?
That would be 6,710.81 miles per hour.
Oh, that is pretty fast. All right. So how do we find acceleration now? Yeah, we just substituted MA for M dot V, right? So we're just going to say the thrust equals MA, so A equals the thrust over the mass. And what is the mass? Yep. So technically, what's that? Yeah. Yeah. Well, I substituted this to that. So in order to find the acceleration, you already know the m dot v, and you just set that equal to ma. Yep.
Did you get
So the 100 kilograms, we're going to assume is kind of neglected, but also it depletes. So say all the gas is gone to that 100, and then okay, go ahead and use it. Yep.
29.4?
Yep. Yeah, 29.4. Yep. Technically, if you wanted to find the acceleration when it first started to the time, you'd have to kind of chop these up, right? Because initially the mass is 3,500, and then whatever, okay? But don't worry about that. Just worry about it after. So we get 29.4 meters per second squared. Yep. All right. So we now know how fast this satellite's accelerating. How do we now find velocity?
Well, what's the velocity from
Not the derivative. Huh?
the
You can multiply by time. Yep. Or if you remember from physics, A is dv dt.
Yeah, I don't think you know that.
But A is a constant, so you already know that V equals V naught plus AT from physics.
And B naught.
And this is why it's 0. That's why it's just times by T. Yep. So this would become 29.4 meters per second squared times 3 seconds. We get 88.2 meters per second.